Hello, Algebra 1 CP students. Hopefully you're having a great day so far. Today, what I'd like to do is continue our discussion on solving systems of linear equations by graphing. I have a few more examples to show you today, including a couple special cases, such as what happens if we graph two lines and they don't intersect at all, or what happens if we graph two lines and they exactly overlap each other. We're going to take a look at a couple examples like that today. But first, what I'd like you to do, going off of yesterday's discussion, I would like you to take just a couple minutes, see if you can pause the video, try to solve this system on your own. Here's two equations in standard form. You should be able to graph both of them and find that intersection point. See if you can do that on your own. Like I said, take a couple minutes, pause the video, and then we'll continue. All right, by now I assume that you paused the video, tried it on your own. I'll go through it with you right now and see how we do. All right, starting with our first one here. Again, in order to solve a system of linear equations by graphing, all you really have to do is just graph both lines on the same coordinate plane and find that intersection point, because that intersection point will contain the x and y value that satisfy both equations simultaneously. So I'll do the first one in green here. Remember, with an equation in standard form, you could choose to find the x and y intercepts, or you could choose to convert to y equals mx plus b. I'll do this one by converting. So if I have this standard form equation, I'm trying to get it to be y equals mx plus b, right? What I have is I'm starting with 2x minus y is equal to 3. I want to get y by itself. So in order to accomplish that, I would subtract 2x from both sides, giving me the opposite of y, or negative 1 times y, is equal to negative 2x plus 3. And now, in order to get rid of that lingering negative sign, just like if there were a 2 in front of the y, we would divide by 2. This negative means there's really a negative 1 in front of the y, so I'm going to divide everything by negative 1. And that gives us here that y is equal to negative 2 divided by negative 1, positive 2x minus 3. And so what does that look like? We'll start at negative 3 on our y-axis here, the y-intercept, and travel up 2 over 1 following our slope. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. If we wanted to extend it in the other direction, we'd follow the slope in reverse to preserve that straight line pattern, and we'd end up with our lovely line. Trying to draw it nice and neat here. I think this will be pretty good. Just like that. Okay. Next, we want to graph our second line on the coordinate plane as well. So dealing with 3x plus 2y is equal to 8. I'll do this one in red. This one I'll try to do finding x and y intercepts, just to show you the two approaches. Again, you could do whatever strategy you want. You could convert this to y equals mx plus b if you wanted to, but just to show you the different approach. In order to find the x and y intercepts, if I wanted to find the y intercept, we'll do that one first. We would set x equal to 0. So that would mean we'd get 3 times 0 plus 2y is equal to 8. If 2y is equal to 8, then y is equal to 4. Meaning that your y-intercept is at the point 0, 4, right here. To find the x-intercept, I would have to set y equal to 0. And we would get that 3x plus 2 times y is equal to 8. That means that, 2 times 0, because y is 0, is equal to 8. 2 times 0 is 0, so we just get 3x is equal to 8. If I divide both sides by 3, I get that x equals 8/3, which is the same as 2 2/3, right? Or 2.6 repeating if you want to think of it that way. But we can just leave it as the improper fraction if you want. 8/3, again, 2 2/3. Let's see, here's 2, here's 3. So 2 2/3 is going to be just about there. Trying to graph it as accurately as possible. And now we can go ahead and join those two intercepts together, and we get a line that looks like this. Okay? And based on our work there, you should be able to very clearly see the intersection point of the two lines. The intersection point is right here. This is at the coordinate 2, 1, and that is going to be the x and y value that satisfy the system of equations. So I'd be able to say that my solution to this system is 2, 1. Okay? Hopefully no questions on that, but that should be a nice recap and review of how to solve a system of linear equations by graphing. Couple other examples I want to show you. What if you're dealing with vertical lines and horizontal lines? Well, nothing really changes in that case, but I do want to show them to you just for the sake of presenting them. So if I have y equals negative 4, and I also have y equals negative 4x plus 4. Coincidentally, a lot of 4s. So if I were to deal with something like that, notice this is in y equals mx plus b, so we can go ahead and graph that very quickly. And this first one, if you notice, y equals negative 4. Remember, when we have y is equal to a constant, right, y is equal to any number, that really just creates a horizontal line at that vertical position. Y equals negative 4 means you have, I'll do it in green again, a y-intercept of negative 4. It's right here. And it's just going to, it has a slope of 0, so it's just going to proceed horizontally from there. It's just right here, horizontal line. Y equals negative 4x plus 4 is in y equals mx plus b. So again, we can graph that by finding my y-intercept, 1, 2, 3, 4 right here. Following my slope of negative 4 means I'm going to go down 1, 2, 3, 4 and over 1. Down 1, 2, 3, 4 and over 1. 1, 2, 3, 4 over 1. And we'd eventually see our intersection point show up right here. Right like this. And we see that intersection point right there, which means that the solution to this system of equations would be 2, negative 4. That's the intersection point of the lines. All right. So if we have a horizontal line, if you notice, nothing really changed. It just so happens that one of our graphs is just straight across like this, but nothing is really different. And the same thing if we have a vertical line, right? If we have a vertical line, you should be able to see that nothing changes either. Suppose we have x equals negative 4, and we have y equals 3/4 times x plus 2. Right? Suppose we had something like this. I'll do that one right down here. In this little area here. Should be enough room, though. Should be enough room. Just like if we have y is equal to a constant, remember when we have x equals negative 4, that creates a vertical line that passes through the intercept of negative 4. Right here. Do you see that? X equals negative 4. That's our x-intercept. So it's going to create that vertical line that passes through that position. Like so. And then my other line here, y equals 3/4 x plus 2, we can just go ahead and graph. The slope would mean that I have to go up 3 and over 4. So up 1, 2, 3 over 1, 2, 3, 4 right there. If I want to extend it in the other direction, we could follow the slope in reverse. Down 1, 2, 3 over 1, 2, 3, 4 right there. And we'd be able to find our intersection point very, very quickly. It would cross right there with that green line that we wrote. And there we go. We find that our intersection point is here. Therefore, the solution to my system of equations is exactly where that green line meets that red line. It's at the point of negative 1, 2, 3, 4, comma, negative 1. Negative 4, negative 1. All right. I feel like, I wonder if the YouTube algorithm's going to think I'm talking about the Boston T stations when I talk about the green line meeting the red line. I know that's a bad joke, but I can't help but think about it in my head. In any case, notice that, again, vertical and horizontal lines, not really any different when we're dealing with graphing systems of equations. But notice that it does give you one of your answers right away. If it's saying y is negative 4 and y equals all of this stuff, well, negative 4 ends up being our solution for y. It's like we're giving you one right away. It's almost a little easier when you're dealing with vertical lines or horizontal lines. Here, same deal. X is negative 4. Well, x was negative 4 in our solution. It's giving you one of those answers right away and asking you to find, hey, where does this graph cross vertically? All right. So I just wanted to show you those examples just for the sake of seeing them, so you know that they are expected of you come any sort of assessment in the future. All right, that being said, let's take a look at a couple of special cases now. What if my lines do not intersect at all? Let's take a look and find out. What if my lines don't intersect? If they just are parallel to each other, right? That would be the only way that lines would never intersect, is if they are parallel. Good example of that is we have something like this. Y equals 2/3 times x minus 3, and y equals 2/3 times x plus 3. And you're asked to find the solution to this system of equations. Well, I have a lot of things to say about this right away. First of all, you should notice that this system of equations will not really make a lot of sense. How could you say that y is equal to 2/3 times some number minus 3, and at the same time, that same y is equal to 2/3 times some number plus 3 times the same number plus 3? How can you take some value, subtract 3, take that same value, add 3, and end up with the same number? It's impossible. This is clearly going to be different than this. So that right away is a little indication that there really isn't going to be a solution to this system of equations. It's not possible to find one singular value for x and y that makes this work. However, what we can notice is really see the same thing by graphing. Kind of a cool connection. As explained, we solve systems of equations by graphing by checking for that intersection point, right? I want to find where do these graphs intersect. Well, look at what happens. Notice these have the same slope, therefore they'd be parallel. If I graph the first one in green, y equals 2/3 x minus 3. It's going to be y-intercept here. Follow the slope up 2/3, up 2/3. If I extend in the other direction, down 2, left 3. Take a look at what happens. Get a nice line there. And how about the other one? Y equals 2/3 x plus 3. Well, kind of the same thing. I'm going to start at my y-intercept of positive 3. I'm going to go up 2/1, 2, 3. Up 2/1, 2, 3. If I extend in the other direction, I could go down 2/1, 2, 3. And notice that these two lines, the red line and the green line here, are parallel to each other. So when will they intersect? The answer is they will never intersect. So if you end up with two parallel lines, a situation like this, this system of equations has no solution, which you could denote by writing the words no solution, or by using the symbol we talked about in class, that sort of 0 with the line through it. Okay, that has no solution. And again, the reason is because there is no intersection point. These lines are parallel. And you could tell that they're parallel because they have the same slope. Right? See how they have the same slope? Both same slope, but different y-intercepts means they're never going to intersect. Okay, so that's something that you have to be aware of. I'll show you another example of that no solution case in standard form. So if we look at a problem in standard form, maybe something like this. Let me draw my graph first. Suppose we had y equals, oh sorry, not y equals. I want to do this one in standard form, my fault. How about the opposite of x plus y is equal to 1, and the opposite of x plus y is equal to -5. Something that's kind of cool, again, is you kind of see that pattern of these two pieces are the same, right? I'm taking the opposite of a number and adding another number to it and getting 1. But I'm also telling you that I can somehow take the opposite of that same number, add this same number, and yet get something different. It doesn't make any sense logically that that should be able to occur. And in fact, it can't. When I go ahead and graph these, we would find that they have no solution. If I want to convert to y equals mx plus b, again, I'll do the top one in green. It's really only one step in order to do that. I'm starting with the opposite of x plus y is equal to 1. I could add x over to the other side to move it and eliminate it from the left, giving me y is equal to x plus 1. That's going to look like this. Y-intercept at positive 1. The slope is up 1/1, up 1/1. Can extend it to the left as well. It's going to look like this. Just like, it's not my best work, but kind of like that. That was actually not my best work at all. Geez, that was great. That was not great. So now the other one is going to be very, very similar, starting with the opposite of x plus y is equal to negative 5. Oh, I'm all flustered after that terrible graph. I have to redeem myself with this one. I would add x to both sides to eliminate it from the left, move it over to the right. We get y is equal to x minus 5. That's going to be y-intercept of negative 5. 1, 2, 3, 4, 5 right here. Up 1 over 1, up 1 over 1, up 1 over 1. Down 1, left 1, down 1, left 1. It's the same slope of 1. It's going to look like this. And once again, you will see that this has no solution. Pressure's on, pressure's on. There we go. Much better. Much better. Lines are parallel. They don't intersect. No solution. All right. Hopefully that makes sense as to why that's the case. One last thing I want to show you is just like with equations and inequalities, we saw some problems that gave us no solution as well as some problems that gave us infinitely many solutions, which we referred to as having a solution set of all real numbers. That's what we said for our answer. Is that possible to get with systems of equations? Well, the answer is yes. You could probably tell by my leading question that the answer is, of course, yes. It's kind of sneaky as to how that happens, though. Take a look at a problem like this. Ready? If I have negative 2x plus y is equal to negative 1, and suppose I have negative 6x plus 3y is equal to negative 3. See that? It may not be obvious right off the bat that this is a special case. So you may go ahead and try to just proceed and solve it, right? If I were to do that normally, I could, let's see, find x and y intercepts. If I wanted to find x and y intercepts of the first one, I could say, well, let's find the x-intercept by setting y equal to 0, meaning I would get that negative 2x plus 0 should equal negative 1. And if negative 2 times something is equal to negative 1, that something must be 1/2. And so your x-intercept would be 1/2 or 0.5 comma 0. Right? Think of divide both sides by negative 2. You'd get x equals 1/2. To find your y-intercept, we're going to set x equal to 0 in this case. We would get negative 2 times 0 plus y is equal to negative 1. Well, this one's pretty easy. Negative 2 times 0 is 0, so we just get y equals negative 1. Meaning our y-intercept is at 0 comma negative 1, like that. And so representing that on a coordinate plane, we would see here that, let's see. We got a graph. We got another graph. 1/2 comma 0, where is that located? That's located right here. 0 comma negative 1 right here. I would go ahead and connect these two together. They're kind of close together. I should have zoomed them in a little bit more, but that's all right. It should look something kind of like this. Yeah, that looks like a good spot. There we go. Nice. Trying to be as exact as I can here. If I were to now do the graph, the second graph, which I'll do in red, graph the second linear function, we have negative 6x plus 3y is equal to negative 3. If I wanted to find the x and y intercepts, I could say, well, my x-intercept is when y is equal to 0, because any point on the x-axis has a y-coordinate of 0. When I do that, I would get negative 6x plus 3 times 0 is equal to negative 3. That means that negative 6x would equal negative 3. And dividing both sides by negative 6, I'd get x equals 1/2. All right, well, no worries. Let's try to do our y-intercept. Maybe that is the intersection point, right? Let's try to do our y-intercept. To find the y-intercept, we would set x equal to 0, meaning we would get that negative 6 times 0 plus 3y is equal to negative 3. And if 3y is equal to negative 3, I would get that y is equal to negative 1. Wait a minute. That's the same thing that we got up there. So what this means is that this is really the same line in disguise. A way that you might have been able to tell that right at the start is you could have noticed that, hey, this second equation is just the first one with everything multiplied by 3. Do you see how it's just everything tripled? Times 3, times 3, times 3. So if you notice that that's the case, and if you notice that when you're graphing, your lines are really the same line, they overlap each other exactly, or you really notice that one of the equations is a multiple of the other. See how this one is just take this first one and multiply everything by 3. Then the question of where do the graphs intersect has infinitely many answers. They intersect everywhere. Sorry, I have to edit myself because I was getting excited in my rant that I accidentally said something wrong a little bit later in this video. I originally said that this would therefore have a solution of all real numbers. That's not the case because it's only points that are on this line that serve as solutions. So we would say that this system of equations has infinitely many solutions, or you could say it's an infinite number of solutions. Sometimes the shorthand of just an infinity symbol is used to represent a system that has an infinite number of solutions, but the original terminology I used in this video was all real numbers, and I want to make it very clear that that is not all real numbers. Okay? Because all real numbers would mean any number for x and any number for y, which is not the case. A point up here would not satisfy the equation. It's just any point along this line. There are an infinite number of intersection points. Sorry for that, and sorry for the poor editing job here that I'm sure will take place. But I hope that makes sense. I hope it is understandable why it wouldn't be all real numbers, but why there would still be an infinite number of solutions. Just a quick little recap. We talked about today a regular old system of equations that we solved by graphing, nice do now problem. We saw what happened if you have a vertical line or a horizontal line. Really nothing else. If anything, these are a little easier, I think, because this is so fast to graph and that's so quick to graph if you recognize that this is a horizontal line and this is a vertical line. We saw a couple of special cases where we were dealing with parallel lines that never intersected. Therefore, there would be no valid solution for them. And lastly, we saw an example of a problem that has infinitely many solutions. Thank you so much for your attention and focus today. I do have a couple of practice problems on Google Classroom that you should definitely give a shot to give your best effort to try them out. But other than that, have a fantastic day. All right. Take care, everyone.